both of those. I think you'll find these much more straightforward than some of the other recent assignments. And after I finish the homework 8 material, I'll go straight to homework 10 material, maybe by the end of today. Okay, any questions before I get started? Administrative and logistical type stuff. Okay, so we were talking about refraction. So when light passes from one material to another, the n value, the index of refraction, can change. That's what tells you about the speed change. So remember that the index of refraction is the divider of how the light speed is in the material versus a vacuum. And we talked about when you go into a higher end material, light slows down, and by the principle of least time, it must also bend toward the normal. So if we measure the incident angle and the refracted angle, we will find that the refracted angle is smaller. Think of it as if n increases, theta decreases. If instead you go from a higher end to a lower end material, it bends the other way. So you bend away from the normal. Theta t is bigger than theta I. Think of it as n goes down, theta goes up. These are things that you should have by second nature, bending towards or away from the normal. These are the concepts that you want to hold on to in more challenging problems. Bending toward the normal when you go into a higher end material, bending away from the normal when you go into a lower end material. The actual law mathematically looks like this. The sine function might seem to convolute a little bit more, but remember that the sine function in the range of angles we're talking about, which is just 0 to 90, isn't really that big of a deal. It just grows. And so if you want to even eliminate the sine function and just think of it in terms of rough relationships, you can think of it as sort of as like the product has to be conserved. Now don't try to use that for actual computation, because it's obviously needs the sine function to be correct for that. But this is supposed to show you that when this goes up, this goes down. Okay? And vice versa. So what I'd like to do today is continue on this thread. First, let's just talk concepts. So I want to give you a couple conceptual examples of where you see this. Here's one. Let's say you have a body of water like a fountain, like so. And you're over here. This is your physics eyeball. Okay? And you're looking at a coin at the bottom of the fountain. Now, if the fountain was empty, you could, of course, still see the coin. Why is that? Well, when the coin is not the source of its own light, it's reflecting sunlight, right, or some other light source. So light is coming down into here. And then I'm going to just show, of course, that going off in all directions, you will have light beams. So if you had a bunch of people standing around all different vantage points, they could look down and see the coin. As long as nothing was blocking the view, they could see one of those. So the light beam that would normally be the one you observe is this one, which would come straight from the object to your eye. That would be if the fountain was empty. However, that is not what's going to happen here. And the reason why is because in going from the water to the air, we're going to have a bend. So we're going from water to air. So you have to be careful here because obviously it's upside down compared to these pictures. But anytime you go from water to air, that would be like this, water to air, light bends away from the normal. So if we went ahead and we dropped in our normal here, the path of this particular light beam, we measure the angle relative to the normal here, and it makes a larger angle to the normal. So it is going to actually get deflected downward. It will not go in your eye anymore. That light beam will still arrive at you. Maybe it hits you in the stomach somewhere. But that is not going to be an observable light beam to you. It has to pass into your eye. So that doesn't mean you can't see the coin at all. It just means you see a different light beam. So for instance, this one before, if there were no water here, this one would have just gone up into the sky, and you wouldn't have been able to observe it. But now, the fact that it gets deflected away from the normal can actually bend it into your eye. So again, if we measure angles to respect to the normal, this angle is going to be theta I, and this angle is going to be theta t, and it's going to be larger, bending away from the normal. So you'll still be able to see that coin, because there's, of course, a whole variety of light beams coming off of it, and even if they all get bent, one of them will get bent just right so that you can actually still observe it, okay? The difference will be is the apparent location, because one of the guiding principles of your whole optical system, as much as you might be evolved and have a neocortex and stuff like that and think, okay, like I know it's not really there, your lower brain can't help but think that whatever light comes in your eye came straight from the source. That's how you can be fooled by things like mirrors, okay? Because your eye has this basic structure where whatever light beam comes straight in, that's where it thinks that the thing came from. So it will naturally take this length right here and just naturally put it right here instead. So notice that your eye basically straightens out the path. If you had a light beam that went like this and then came into your eye like this, your eye would just naturally trace it back, okay? So essentially, your perception of the situation is that the path is straightened out, okay? So what does that mean? Well, you see the coin in a slightly different place than it actually is. Notice that it is far more shallower, right? Instead of looking like it's this deep, it looks like it's this deep. And that will not only hold true of this coin, it will hold true of every coin at the bottom of the fountain. It will hold true for the bottom of the fountain itself. So this body of water will look shallower than it really is. Has anyone ever experienced this? Where you look at a body of water and it looks like a different depth than it actually is? I know when I say go to make myself some, I'm going to need those clothes a little bit later for the demo. So.
That's okay,
Yeah, I'll let you know. If we go to, if I go to say make myself some pasta and I fill a pot full of water, right? I'm trying to make it deep enough so that the pasta can get in there. So and then I go to put it on the stove and I go, is that enough water? Oh yeah, refraction, right? Because you think it's shallower than it really is, especially when you're viewing it from an angle like this. You may have noticed, when you're wading around in a body of water, you look down and you have these like stumpy short feet or legs, right? That's the same effect, okay? So that's just the bending of water, or bending of light as it passes from the water to the air. And again, because it's bending away from the normal as it emerges, that is what gives the lift to the bottom surface and makes you think that the object is not really where it is. So there's one very important conceptual question where you're looking at a fish like this and you're trying various ways to catch it, and the question then just becomes, where is the fish really compared to where you see it? Okay. Okay. So that's some of the concepts, and I think I'm going to. I guess let me give you an alternate. Oh, do I want to? I'm going to give you an alternate way to reason refraction, which is more useful in some applications. But let me not do that right now. Let me show you the demo where I show you this stuff. I guess let me go ahead and see if I can get the lights off. Where's that light? Oh yeah. Okay. Okay, so here's what I have. I have a tank of water. It's halfway full. So there's air in the top half and there's water in the bottom half, and then I have a light source up here. So first of all, I'm going to send the light directly down, like this. Okay? So one of the things you notice right away is that it goes in at 0 degrees to the normal, and it also emerges that way. Okay? So I guess that the first thing I should mention before, I might have forgotten to do this. I could have done it last time, but I'll do it now, is that there is no bending at the initial angle is 0. Okay? And if you think about it, it makes a lot of sense because here, you should go straight through. The principle of least time here is that light should go from one point to another in the fastest possible time. Well, here the fastest possible time is also the shortest distance, which is a straight line. No other way, right, something like that, that could not improve upon it. That would be more distance and more time. So one of the important things to understand is that the whole principle of least time does require that the bending starts when the incident angle is bigger than nothing. So if the incident angle is bigger than nothing, then it's possible, or I should say it is the case, that the shortest time is not the shortest distance, which is what we talked about last time. And that's what causes the bending. The light prefers to take the shortest amount of possible time. So right now I've kind of set up the baseline case in my demo. You can see that there is no bending of the light whatsoever. Okay? So I don't know how easy this is to see, but there is no bending of the light, it goes straight through. So now let's increase the angle. This conveniently has the angle from the normal already marked, so let me increase the angle to say 20 degrees. So it's 20 degrees up here, and hopefully you see that the light does bend toward the normal, okay? So even though the incoming angle is 20 degrees, this is only about 15 or so. And you could calculate that exactly using the end value of air and the end value of water. So let me try a different angle. Let me crank this up to 50 degrees. So the incident angle is 50 degrees. And the outgoing angle is, looks like 35 or so. Okay, so it is bending toward the normal, right? And I can go all the way up here to say, I don't know, I can go to 70 degrees. You'll notice that, by the way, that the outgoing beam is getting fainter. So remember that we are not able to calculate the amount of intensity that goes to the reflected and refracted beam. We can say the energy is all there. But hopefully, if you can still see it, even though it's very faint, the incoming angle is 70 degrees, and the outgoing is only 40-something. Okay? So that's the case of bending toward the normal, going into a higher end. Now let's do the opposite case. This is actually going to be very similar to my fountain example because I'm going to go from higher end to lower end, but the higher end is going to be the bottom, right? So I'm starting here and I'm going here. The reason why I do it here is the same reason it's true in a fountain, okay? Water tends to be on the bottom, right? I can't take this water and lift it up to the top half and leave air in the bottom half, but I can shoot the light up from underneath. So now I'm going from water in the bottom half to air in the top half, right? And once again, you see, there's no bending at all yet. It just goes straight through, right? So let's now try something different. Let's go to 20 degrees. So I'm 20 degrees on the incident side, and you can hopefully see it bending away from the normal. Away from the normal, it's going at 30-something, okay? So it is bending away from the normal, okay? Let me try increasing the angle a little bit more. Let's go to, I don't know, 40 degrees. So I'm 40 degrees from the normal on the incident side. It's going 60 or so on the way out. It's bending away from the normal. Okay? Let me go a little further. Now here, you might actually notice that both beams are there. That's because the intensity of the two is roughly comparable, so they're both hopefully bright enough to see. So you do see them both the reflected and refracted beam. So sometimes one is too faint to see, especially because I can't really get it too dark in here. But generally speaking, there are both. There is both a reflected and a refracted beam. Some percentage of the energy goes to each one. That percentage changes, so sometimes you can't even see one of them. But there are both in general. Okay? However, the next thing I want to talk to you about is that there's a special thing that can happen if you're bending away from the normal. If you're bending away from the normal, what that means is that the outgoing beam, since it's always making a larger angle, that can actually get to 90 before this does. Okay? So what happens then? So let's try it. So right now I'm pretty close. Look at the incoming beam is coming in at 45 degrees or so, and this is like over 70 degrees. So I'm going to see what happens when I increase the incident angle even more, and then notice what happens. As that refracted beam goes to 90 degrees, it also disappears. So now 100% of the light is actually in the reflected beam. The refracted beam has disappeared. We bent it so far away from the normal that it didn't actually go into the other material. It didn't pass up into the air. There is no beam that's emerging from the water. Okay? It's all still there. Okay? So I'm going to even dip my finger in here. You should see it light up, right? Like ET or something. Okay? The beam is there, but that's because I'm putting my tip of my finger in the water. If I pull it out, there's no light that hits it. That's because in this case, 100% of the light is actually being reflected. It does not at all come out. Okay? So that's the next thing I'm going to talk about. That's called total internal reflection. That's a special case that we need to be aware of. It has many useful applications. Okay? So let's do that. So let's talk about total internal reflection. TIR for short. So a couple important things. This whole phenomenon relies upon the fact that you're bending away from the normal. So it's only possible when the Ni is greater than Nt. You could never have it unless you bend away from the normal. So Ni has to be bigger than Nt. So what happens? Well, if you are shooting it with an incident angle of nothing, it goes straight through. If you increase the incident angle a little bit, then this will be even bigger. So it's going to bend away from the normal. Remember that the transmitted angle or refracted angle grows faster than the incident angle because you always have to have the transmitted angle be larger. You have to bend away. This works when you can bend away from the normal. And at some point, and I'll draw the case in green, at some point, this becomes large enough that this literally bends to 90 degrees. Now, I should, of course, mention that I've been drawing the refracted beam, but all of these cases would also have a reflected beam. Here, it's really important to remember that there's a reflected beam. This is the reflected refracted, because it turns out that when this refracted beam gets bent so far from the normal that it's 90 degrees from the normal, so basically it never really escapes into the second material. It's in this limbo land, kind of skirting. You might ask, what happens? Does this just skirt the interface between the materials forever? Well, no. In fact, rather than be in limbo here between the two materials, this beam actually doesn't exist. 100% of the intensity goes here. That's why we call it total reflection, because 100% of the light energy becomes reflected. Hence the name total reflection. This is the one case where I expect you to know the percentages of the light that are incoming going out to the reflected and refracted beams. Generally, it's some split. That split is not always even. You saw when I did it with this tank here that sometimes you can see one beam and sometimes you can see the other, sometimes both. This is the one case where I expect you to know that 100% of the light is reflected. The refracted beam, basically, when it gets bent to 90, it also disappears. It doesn't exist anymore. Okay, so this doesn't really exist anymore. Okay. The reason why it is called total internal reflection is because oftentimes this N here is somehow internal to some kind of substance, and the smaller N that you are not escaping to might be the air or otherwise outside environment. So really, we're totally reflecting the beam such as to keep it inside or internal to the first material. Okay? So let's work out the math for this. We can do that. We have the equation. So the transmitted angle has gone to 90. So this angle right here is 90 now. We give a special name to this incident angle so we don't mix it up with the general incident angle. We call it the critical angle. So when we have increased the incident angle up to the critical angle, the transmitted angle has gone to 90, which means we have achieved total internal reflection. Okay? So we can solve here. Sine of theta critical is equal to nt over ni because sine of 90 is 1. Okay? So that is the expression for the critical angle. Now, if you want the critical angle by itself, you can certainly take the inverse sine of both sides, but I think it looks ugly, so I'm going to leave it like that. You can always solve for it numerically. Okay? So this is the critical angle. Nt, this is the material that you're trying but don't actually refract into, that you don't go into. And this is the material that you stay in. So ironically, the material that you never had a chance to get into still factors into the equation. And it makes sense that it should, because if the n value wasn't changing, then you wouldn't reflect at all. You're just not going to randomly reflect in the middle of a material. So it's the running into the lower end material that causes the reflection, but it is 100% reflection. So none of the material, none of the light actually emerges into this. Okay? So that's the critical angle. And I guess I should show you. You might be wondering what happens if we go above the critical angle. So let me show you that real quick. I forgot to do that. So right now, I'm at the critical angle. You might ask, well, if now this is a large enough incident angle, what about if I increase it some more? Well, it is maintained. So once you have achieved total internal reflection by increasing the angle to a large enough value, the incident angle, that is where it'll stay there. Okay? So the critical angle is just the minimum bar to clear. It's where the party starts. Okay? So total internal reflection occurs for any incident angle that either meets or exceeds the critical angle. So this right here is kind of what you need to know as far as the equations go. So common mistake that students make, they can solve the equation to get the critical angle, but then they think that it has to be that special angle. Not so. That is just the minimum bar you need to clear. Any angle that's bigger than that also will exhibit this phenomenon, okay? Okay, so let me talk about some conceptual things to piggyback on top of this. So if you have an ever so slight end difference, so this is slightly larger and this is slightly smaller,